Hi there, everyone. Thank you very much for joining us today for our webinar on validating time-sensitive networking in automotive Ethernet networks. We thank you for your attendance and participation. If you have any feedback or other webinar topic suggestions, then please let me know by chat, or you can email me later at marketing@testforce.com. Before we get started, I'd just like to let everyone know that this webinar will be recorded and you'll be receiving an email afterwards with a copy of the recording. So you can go ahead and share it with anyone you think would be interested or rewatch it if you'd like. If you're interested in any of the other webinars we'll be hosting coming up, or to download any of the free resources we have available, such as white papers or application notes, then please go ahead and visit testforcecc.com/academy and you'll find everything you need right there. If during the webinar you have any questions, make sure you ask them in the Q&A section in the right side menu bar, and we will be sure to get to all of those questions as we come to the end of the presentation. And now, without further ado, let's jump right in and talk about time-sensitive networks with Avik.
Thank you all for joining us today. I am Avik Bhattacharya from the Keysight product management team, and my focus area is automotive and industrial Ethernet. I have worked on the networking industry for more than a decade now, and I have seen many disruptive technologies in the networking domain. Automotive Ethernet and time-sensitive networking is one of the recent and major ones. In this session, we are going to take a look at the technologies which are enabling in-car network infrastructure for the future of automobiles. We will discuss the market trends that are taking us towards an automotive Ethernet-based communication system inside the vehicle. In those networks, application of time-sensitive networking, or TSN, enables the time-critical applications to run seamlessly. In the second part of the discussion, we will try to understand the TSN ecosystem. We will talk about the different TSN standards and what are their goals. As with any new technology, adoption of TSN and making sure that the applications work fine with it throws a lot of challenges for the validation engineers. In the final section, we will discuss a few validation challenges and the methodologies to tackle them. All in all, it should take us around 30 to 35 minutes to cover these topics. Afterwards, I will hand it back over to our moderator and answer a few questions. Now, if we look at the major trends of the automotive world, the ultimate goal is the autonomous car, offering multitude of benefits to the driver with not only convenience driven by luxury, but also safety. To the environment, saving energy, possible alternative energy to gasoline and reducing emissions, and finally for the society as a whole, to try and address the 1.23 million road deaths that happen every year worldwide. And all of these components, which is shown in this slide, like electric vehicle, connected car, autonomous drive, and shared riding, they help achieving that final goal. The automotive industry is accelerating its electronic technology revolution and fusing with the clean energy ecosystem. By 2020, 90% of the cars are expected to be connected, and by 2023, 30% will be electric. One of the most ambitious areas of automotive innovation is autonomous driving. Advanced Driver Assistance Systems, or otherwise called as ADAS, for current mainstream human-driven vehicles and autonomous driving systems in prototype stage are dramatically improving safety and will save many lives. And it isn't just us saying it or wishing it. And we are not here to argue when. The point is, it is going to happen. And the technology innovation is already underway. To support all these sophisticated applications like ADAS or high bandwidth infotainment system, the underlying communication network needs to be redesigned. Automotive Ethernet and time-sensitive networking is paving the way for the next generation in-car network infrastructure. So let us take a step back and look at the evolution introduced by Ethernet as a technology. The evolution is not only confined in the automotive industry. Ethernet has made its way to multiple industries outside the traditional IT Internet domain. And the reasons, if we look at, it's the standard-based implementation, which means no vendor lock-in. This is important to reduce the cost in the competitive global market situation. The second is the shared network architecture that it provides, which means coming out of traditional complex point-to-point connections and the amount of cabling that contributes to the weight of the car, for example, reduces significantly. And finally, the higher need for bandwidth in all of these industries, like the infotainment and ADAS in the car network, which the traditional technologies could not provide. The application running in these industries also required determinism that best effort traffic delivery of Ethernet was not suitable for. So, for example, Ethernet was not suitable for low latency or deterministic latency and guaranteed delivery. And therefore, the IEEE 802.1 working group came up with standards that tries to solve these problems for Ethernet. The technologies have evolved based on the requirements from the different industries. So when IEEE started solving this problem, it looked at the need for Pro AV industry, automotive, and also industrial sector. The Pro AV required more bandwidth guarantee. In addition, the automotive required lower latency and determinism. For example, credit-based shaper, which we will discuss later, could address that. And on the other hand, industrial application brought the need for even more determinism and sub-microsecond latencies. So, which gives the birth for time-aware shaper, again, something we will discuss later. Also, the shared networking philosophy required different applications sending the network. Mix of multiple traffic could hamper the low latency in the network, and it requires things like frame preemption. The IEEE working group started as the AVB working group, and then it changed its name from AVB to TSN to cater to more generic demand coming from these industries. This slide shows the number of Ethernet ports in millions that are going to be inside a car network in future. Yes, the number is pretty staggering, more than 500 million by 2023. And what is driving this? It's the more and more applications inside a car that is going to use Ethernet as the communication medium. It started with infotainment, but right now it's infotainment, ADAS, the backbone, the diagnostic network. So with this, the traffic characteristics are very different for all these applications, which means they are going to have small or large frame size, the time criticality is different, and the bandwidth requirement is very different. And this slide breaks it down further where Ethernet is used today in the car network. The red line denotes the usage of Ethernet as the medium. Of course, what it shows is the usage of Ethernet in today's car network is very limited. Now let's take a look at how it will be used in future. The bottom of the slide indicates how Ethernet will be used tomorrow. And again, if you look at the red lines in the bottom diagram, it shows that the usage is increasing very fast. What this simple diagram shows below is that on the current architecture, you have one Ethernet link from the diagnostic port or DLC to the gateway. However, on future architecture, the gateway will be linked to all the domain control units or DCU through Automotive Ethernet. And this is going to be with a combination of 100 base T1 or also called as 1 TPCE and 1000 base T1 or RTPGE. The diagram in the slide is from a report published by Frost and Sullivan. This shows a typical architecture of an in-vehicular network. As discussed in the previous slide, we can see that ADAS and infotainment are the first adopter of Ethernet in their domain. In this architecture, the ECUs within domain get connected using different communication layers that are commonly used in chassis domain. All domains are connected using central gateway, acting as the backbone of the entire communication network. Each domain has its own domain controller gateway to provide secure communication to vehicle EE network. In a domain control architecture, ECUs are architected in a domain-specific manner, with subcontrollers integrating various functionalities under relevant domain. If we take an example of the central controller network in this case, the network will have data and control traffic from all the domains. The time-critical and not so critical traffic may interfere with each other and cause the more important traffic to get delayed or even dropped. Delay in time-critical application traffic like ADAS can have severe consequences and even fatalities. That's where TSN comes into play to ensure deterministic behavior for the real-time application traffic. Well, all these new technologies make the next generation car network very different from the traditional communication architecture. There is additional complexity at the data link layer as well as at the network layer. As you can see in the slide, there are a lot of new components being introduced in the higher layers. All the leading automotive suppliers that we work with are busy implementing these new set of standards that have evolved to enable Ethernet as the communication medium in the car. I receive a lot of questions about validation methods for these new upcoming standards like AVB or TSN. In the race of being the first to market, the ECU manufacturers are trying to build the latest time-sensitive networking capabilities into their solution. And it must be so difficult for them, for the engineers, to ensure the quality of so many new technologies in a product. In the next few slides, let's take a look at what these technologies are about. What are the AVB TSN ecosystem? So this brings us to the next section, which is where we discuss what is TSN. So before jumping into the individual TSN standards, let's take a look at an example in the car network. This example is hypothetical and simplified for explanation purpose and may not exactly resemble an actual car network scenario. What we see here is a couple of switches which is connecting a temperature sensor sending data to the dashboard. Now this data is periodic in nature, small frame size, but is it super time critical? May not be. Now let's add a few more elements to this network, where the infotainment talker is sending high bandwidth infotainment audio video to the speaker. The infotainment data, as I said, is high bandwidth, and at the same time, the bandwidth guarantee needs to be ensured by the switches in between in order to ensure a good experience of watching. So if it collides with the temperature data which is being passed on the switches need to ensure that it should give priority to the infotainment data. Let's add a few more components. Here we have an ADAS controller which is receiving data from the radar, and based on the data it is taking decisions. Now this data is small frame size, periodic in nature, but super time critical. So a special scheduling needs to be done in the switches to ensure this data is always passed through. Finally, we add an emergency braking system. Now, a collision detection unit in the car detects whether there is any kind of collision possibility in front of the car. But as soon as it detects, it needs to send a signal to the emergency braking system. And this particular signal, when it reaches the switch, if the switch is already transmitting any kind of traffic, that needs to be preempted, because this critical data cannot wait. So there is a need for preempting traffic in this type of a network. And finally, if we look at the network design, it all depends on the one connection between the two switches. But what happens if that particular link fails? So there is a need for replication to ensure more robustness in the network. For example, what we see in the picture, the temperature sensor data can be replicated over two links and sent to the second switch. TSN, which stands for Time Sensitive Networking, is the name of the IEEE 802.1 task group responsible for the standards at the data link layer for solving the time-critical applications problems. The time-sensitive networking set of standards are under development by this networking task group, and the TSN task group was formed in November 2012 by renaming the existing audio-video bridging task group. The name changed as the result of the extension of the working area of the standardization group. The standards here try to solve, for example, the problems defined in the previous slide. The standard defines mechanisms for the time-sensitive transmission of data over deterministic Ethernet networks and provides solution for things like reservation, traffic shaping, time synchronization, redundancy, and preemption. The AVB standards were the first wave of the AVB TSN standards. 802.1BA, or the audio video bridging systems, defines a profile of standards needed for audio video. 802.1BA defines some limits to ensure the target application's performance, prevents 99.99% of dropped frames caused by congestion by supporting stream reservation with guaranteed bandwidth and deterministic latency. The IEEE 802.1AF, or timing and synchronization, the IEEE 802.1QBV, or credit-based shaper, IEEE 802.1QAT, a stream reservation protocol, and other applicable standards. The 1722 provides the AVTP encapsulation, or the audio video transport protocol. And finally, the 1722.1 2013, which is also called the AVDCC, or audio video discovery enumeration protocol. The 802.1QBV is designed to achieve the theoretical lowest possible latency in an engineered network. As per the standard, the forwarder adds time gates on each queue on a port. At specific pre-programmed intervals, a port's lower priority queues can be blocked so that the higher priority traffic can pass through unimpeded. It delivers the lowest possible latency for a stream all the time. Frame preemption is designed to reduce latency of time-sensitive streams in a non-engineered network. It supports one level of preemption where a higher priority frame can interrupt the transmission of a lower priority frame. When the higher priority frame is done, the lower priority frame continues where it left off. Frames must be completely reassembled at the link's receiver before they can continue through the bridge or like an end node. 802.1 QCI aims at ensuring deterministic and known latencies regardless of the network topology. This requires minimum delays per hop, making the network latencies more consistent. The goal of this standard, or it's also known as the per stream filtering and policing, the goal is to able to identify flows by things other than the layer 2 fields. And these identified flows are then assigned to a polisher, so the reception rate is limited. This limit detects misbehaving link partners, protecting the rest of the network. So if any device malfunctions in the network, this protects the rest of the network from the malfunctioning device. The next standard is 802.1 CB, which supports the data redundancy and seamlessly for all the applications. This solves the problem associated with CRC errors, broken wires, or any loose connection when rings or rings connected to a ring networks are used. The time-critical frames are expanded to include a sequence number, and they are replicated where each copy follows a separate path in the network. At any merge point in the network where the separate paths join again, the duplicate frames can be eliminated from the stream. And finally, the 802.1 AS Rev suggests enhancements over the existing 802.1 AS standards or the GPTP mechanisms. This introduces methods for clock redundancy, standby grandmaster, etc. Based on what we have seen in the previous slides, the IEEE 802.1 TSN task group has created standards which are like tools in a toolbox, with more being added all the time. First, you need to know what tools are available, and then you need to learn what each tool does and what its cost is. Implementation of every standard has a cost. And only when you know all this, then you can decide which tools are appropriate for your application. So based on our experience, different industries adopt different methods for designing their time-critical network, and they choose the methods from this toolbox of TSN standards. This is what we have learned from our interaction with our customers across different industries. So I'll take a pause and let you look at the slide. And this brings us to the final part of this session, where we discuss the validation methods of a TSN system. What we are finding is that many ECU manufacturers are focused on validating their solutions in isolation. This is good first setup for unit testing, but what many fail to analyze and quantify is how their solutions are going to behave when integrated in entire car ecosystem. You need to be able to understand and assess the behavior of your solution in a real scenario where the traffic is unpredictable and requires an interplay of other components in the ecosystem, and finally interoperate with the new standards. And from our vast experience of working with the network equipment manufacturers or NEMs, the service providers, and the data centers, what we have learned is that most of the critical failures happen at the system level. An automotive ECU, when put in the real car network, needs to handle communication with ECUs from other vendors, high-scale traffic, and unpredictable behavior caused by the other components of the network. A badly designed component in a network can cause malicious traffic and can even bring down your product, which you have tested in your lab under ideal conditions. Moreover, if the performance of your product has never been benchmarked in the realistic workload that is present in a car network, coming from different components like the advanced driver assistance system or ADAS, or maybe infotainment, engine control, etc., then you cannot guarantee the same performance which your data sheet will mention. Cars today have up to like 100 ECUs and more than 100 million lines of code. And the network is only as strong as the weakest link. A failure of an ECU in a car network can cause fatal implications like cyber attacks, accidents, and potentially a huge loss of goodwill for the company or the component manufacturer. A similar incident prompted Chrysler to recall 1.4 million vehicles in 2016. And as per the report in the BBC News, based on their Q3 results, the same year Chrysler claimed to have incurred a loss of 761 million euros due to the recall campaign. Let's take an example, a very detailed example of what kind of validation is required to catch an error. And of course, this is just one example. There are many, many scenarios like this. So here in the left-hand side of the slide, what we are seeing is for a time-aware shaped traffic, within a gate open interval, the blue frames are supposed to get transmitted. In the scenario 1, all the frames are egressing within that gate open interval, which is the correct scenario, and there is no violation. However, if there is an issue with the accuracy, then the gate fails to close within the configured time, and multiple packets might egress after the gate close event, which is scenario 2 here. And we can see that a couple of orange packets are egressing after the gate close event, which is a window violation. And in the third scenario, even if the final frame starts egressing during the gate close event and extends the gate close event, after the gate closes, the packet keeps on transmitting. That's again a window violation. Now, how do you catch this type of errors on a per packet basis when the traffic is being transmitted at line rate? There are multiple traffic. So you need sophisticated tools to tell you exactly what is happening in the network. The screenshot at the right-hand side is coming from IX Network's TSN solution, where the tool tells you the amount of window violation, the number of packets violating a window, the time for which the violation existed, and many statistics like that. This type of analysis can help you catch errors in realistic traffic scenario. Now let us shift our focus to a system level view in a car network, and let's see what kind of traffics are flowing through that network. The control signals are periodic in nature, small sized frames, and time critical. To handle this type of traffic, it requires time aware shaper. Then the ADAS video stream is high bandwidth, it's large size frames, and high priority since it's for ADAS. So this requires stream reservation and credit-based shaper, but credit-based shaper also has got multiple classes. So this requires a class A. The infotainment audio video is high bandwidth, large size frames, and relatively lower priority than ADAS. But it requires lip syncing. So this can be achieved by credit-based shaper class B. And finally, the diagnostics and file transfer traffic is of variable frame size and lower priority than the others. So for these, best effort delivery mechanism is sufficient. Now for all of these AVB standards to work, the network needs time synchronization in place. So it is obvious that the validation methods also needs to evolve as soon as we start talking at the system level. So gone are the days when the network engineer's focus should be, to validate one particular AVB reservation or if QTSS standalone. I mean, even if a switch or an ECU in an automotive network can handle credit-based shaper and time-aware shaper separately, the real test is running them together. Once the industry has gained confidence with the individual tools IEEE has provided, and we have discussed in our previous slides, now it is time to design the network with these tools. So the challenge is to create real-life simulation of workloads in the lab. The automotive workload scenario is new and it has never been tested like this before. Here is an example of a system-level test, which was conducted using Keysight's IX network solution. In this topology, we can see that the card network is handling two types of traffic. One is the ADAS sensor traffic, which is time critical, and then there is unscheduled Ethernet traffic. The unscheduled Ethernet traffic is going at line rate, even though it's not time critical. And the ADAS sensor traffic has a defined rate, which is 2000 frames per second. So in this topology, we have different TSN standards running, which is being emulated by the test tool IX network. The 802.1as is being used for time synchronization. Then we have the time-aware shaper for the sensor traffic, and we have QAV for the other type of traffic. We did an experiment in our lab a few days back with ECUs from two of the leading manufacturers. We ran tests on the devices with high-scale simulated traffic for infotainment and ADAS, the very same scenario which I discussed in the previous slide. Now, when we ran the two types of traffic independently, both devices worked fine. However, when we started mixing the infotainment and the ADAS traffic, we observed 20 to 30% packet loss in one of the ECUs. And what surprised us is both the ECUs failed to adhere to the latency guarantees that they provided in their specifications. So imagine if you as a ECU manufacturer and you provide your ECUs to an OEM, and then imagine the repercussions if an OEM took your solution into a proof of concept and experienced the similar results. Would you feel confident in the outcome? And you can see the results in the slide. The screenshots are actually taken from the IX network tool, which shows the loss latency characteristics of the traffic. Because of the kind of validation capabilities described in the previous slides of the IX network and IX Anvil test tools from Keysight, the leading car makers have been using these tools for some time now. For example, the BMW Group are successful in validating their automotive Ethernet toolchain and getting visibility into the performance and robustness of their switches integrated in the ECUs using the Keysight's IX Network and IX Anvil solution. To know more about how they are using these tools, you can find a link in the resources to the white paper or the case study. Another example, BYD, an automotive company in China, wanted to deploy 21st century technologies to reduce cost and improve their customers' experience. But they needed absolute confidence that their new open alliance conformance testing and TSN solutions work fine. By using the Keysight solution portfolio, they were able to validate all of the automotive Ethernet test cases necessary while also reducing their test time by almost 50%. Again, a link is provided in the resources to know more about the testing that BYD was doing. IX Network provides the most comprehensive TSN validation solution in the industry. It makes use of the ixia hardware to measure the traffic characteristics in the accuracy level that is required by these industries. It provides coverage for all the TSN standards in the ecosystem, and it not only provides functionality, scale, and performance testing methods, but also provides conformance packages with pre-canned test cases to validate implementation at an early stage. At the same time, it also provides the standard test plans defined by standard bodies like Avenue Alliance, which helps an implementer to prepare for a certification or to ensure the device under test is ready for interoperability with other vendors. We have discussed a few example scenarios in this session about the validating of automotive Ethernet based ecosystem. However, the scenarios are beyond these small examples and vast enough for layer 1 to layer 7. And for all of these scenarios, one requires a test tool to be able to ensure quality of the implementation. Keysight, as of today, is the only company which provides validation solutions spanning across the layer 1 to layer 7. It provides solutions for functionality, conformance, and performance validation. The conformance solution is time-tested. It provides conformance for the Open Alliance, Avenue Alliance, and AUTOSAR-based test plans. There are more than 1,300 test cases for the TCP/IP stack beyond the TSN standards that we talked about. And finally, the powerful test platform, which is coming from ixia, provides the protocol emulation support for AVB TSN at high scale. It provides the realistic data traffic for car workload. And finally, the extensive statistics for identifying and debugging failures, some of which we have seen as an example in the previous slides.
That was great. Thank you, Avik, for presenting today and for the very informative webinar. I'd like to say thank you as well to all of our attendees today who made the time to sit in with us for this webinar and for all of your participation. As I mentioned at the beginning, this webinar was recorded and we'll send out an email with that recording in the next day. We have a new lineup of webinars coming up on our Testforce Academy. So visit testforcecc.com/academy, and we're always open to hearing your suggestions as well. So you can fill out a form there on that page or just check out what else we have in store. And we did have a few questions come into the Q&A section, and we'll be getting back to you by email. I think the one here is much more specific in nature, so I will leave the chat window open for the time being in case anyone else has questions that you'd like to ask. And if any questions come up later, don't hesitate to reply back to my email, or feel free to send a message to marketing@testforce.com and we'll get back to you with the answers or put you in touch with the right person. We've come to the end of the session today, but I look forward to hearing from you all, and I hope that you have a great day. Thanks again and take care.